Okay, so let's look at how this spatial information is encoded in MRI. So we have introduced the fact that we are scanning Fourier or reciprocal space or K-space. This is the frequency direction along X. I'll use the same variables, and along Y the phase encode direction. So along X, we're looking at a gradient here. We're not going to bother again with the dephasing and rephasing for the echo. We're just going to simplify here the diagram, and we have the phase encode gradient. This is our sampled signal that we have here. We are acquiring at this point. So if we apply the phase encode gradient, then we have a ky that's non-zero, and we will encode kx according to the time here. So these are the points in kx. So we have acquired here one line in k space or reciprocal space. We'll repeat it with a different amplitude for the y gradient. Then we encode the second line of k space. The gradient is reduced, so ky is reduced. The third line, and each time this is stored in a two-dimensional matrix. Fourth line, fifth line, sixth line, seventh, eighth, etc. And as we acquire this, and then we do this much faster, and this is the sound that you hear. Bzz, 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 bzz. As you hear this sound from the MRI, this is how the K-space matrix is being filled up. So what we don't have here is the RF pulse. We haven't drawn this, but of course we have an RF pulse each time that we have to apply. And so this means we have one line of K-space that's being acquired per TR. TR being the time between RF pulses. TR, as we have seen, is determined by the longitudinal relaxation time. So it is typically on the order of seconds. The acquisition here, this is typically on the order of milliseconds. So this is very fast done. These data points are fast acquired, and here every line is acquired every TR seconds. So if we are looking for a 256 squared matrix, the read dimension is in milliseconds. That doesn't count. But if we have 256 phase encode directions and we take a typical T1 of 1 second, so a TR is on the order of seconds, then a image matrix, a 256 squared image matrix, it takes roughly 4 minutes to acquire that data. Conclusion: MR scans are long and motion sensitive. They are long because the acquisition has in large part to do with T1, and T1 is not very short. And motion sensitive because if every time you acquire a K-space line here, you acquire information on the entire object. If this part of the matrix does not fit this part of the matrix, then of course they don't reconstruct very well, and this produces a mismatch and therefore motion artifacts. So here's an example of a subject that moved during acquisition. This is a sagittal cut, the nose is here, brainstem is here, so this is the brain, and you can see here these bright areas here, these streaking artifacts. One has ghosting, so-called ghosting, so that's signal that doesn't belong where it is being observed. There is no signal outside of the head, or ringing artifacts that are being observed. So, there's a few things we can say about the image matrix. So the maximum kx or ky that one acquires, that determines the resolution. And the increment, the delta k, that is either the delta kx or delta ky, through the Nyquist theorem, determines the field of view. So if we have closely spaced samples, then one gets a big field of view. If one has lots of samples, one gets a high spatial resolution. So this whole process, since what is being acquired is the Fourier transform of the object, in this process there is, of image reconstruction, there is no influence on the resolution. The resolution is uniform across the entire image, and also the sensitivity as such, once the signal is acquired, the reconstruction process induces a uniform sensitivity. So in principle we could acquire an image with 8,192 pixels in one direction and 192 pixels. In the other direction, we are not limited from the acquisition process to the size of the matrix. However, the limitation that we encounter is the voxel magnetization. As we have seen a few weeks ago, the sensitivity is limited by is maximal for thermodynamic equilibrium magnetization, and that is determined by the magnetization in the voxel. That's the number of molecules, etc. So there is the fundamental limit. We have in the K-space matrix, we have one particular point to consider, and that's where Kx and Ky are equal to 0. That's the center of K-space. At this point, Kx and Ky are 0, and this point is of particular interest. That's where the image is maximal. We have no dephasing in any direction of the magnetization. Let's look at the properties of the K-space matrix. Here is an image of an MRI, the data acquired at 512 by 512 spatial resolution. That's the reconstructed image. That's the 2D Fourier transform. That's XY space, and this is K space here, Kx, Ky. If we now take the center 8 points, 8 by 8, and reconstruct this, we are getting a very blurry image. If we take the image and we eliminate those central 8 points, we get more or less the sharper features of the object. We do the same thing now with just taking the first 16 points at the center, reconstruct, and here we eliminate the central 16 by 16 points, and we're starting to see the edges here, and here we're starting to see some of the structure. 32 by 32, and it's already quite amazing how much contrast we have at this point. 32 by 32, that's a very small matrix compared to 512. We're starting to see already structures here in this brain scan, and eliminating the first central 32 points gives edge features. Now, the one thing that we have to bear in mind is that the center K-space point determines the contrast of the image. And this comes from the center of the K-space, that's S00, Kx and Ky equals 0, is given by this expression here with Kx equals 0 and Ky equals 0. So this is the Fourier transform of the magnetization. That's what we are detecting. If we look at the discrete Fourier transformation, at the discrete Fourier transformation we employ the fact here that it is periodic over the sample time period, and we can do a time shift. With a time shift, so here's the signal, that's the echo that we record. We can, in discrete Fourier transformation, this signal is going to be the same signal here in magnitude as this signal. So we've taken this half, shifted it to the left, and that half, as we shift, we fold it around and put it on this side. And now we have seen at before, for the Fourier transformation, that the signal at time 0 is proportional to the magnetization. Here's our time signal, 0. So this signal here is proportional to the magnetization, and therefore is proportional to equilibrium magnetization and the effects of relaxation. Okay, let's go on. We have 64 by 64. The image gets sharper, and we are getting more and more. What's outside of the 64 by 64 are very sharp features. The high frequency component, 128 times 128. We're really now only seeing the sharp edges, and here the image is almost the same quality as this image here, and we are left with very sharp features. So what this means in terms of data acquisition, if your subject moves here in these close to the central K-space points, you're going to have a fairly big impact on the image, whereas if it moves here at the edges, where there's very little signal here out here, the impact is much less. So crossing through the 0 K-space point defines the contrast and also the magnitude of the motion artifacts. Okay, I want to summarize the spatial encoding with the gradients. I'll try here this depiction that is more on a mathematical basis. So we'll have here the RF pulse, that's done by the B1. We have a flip angle alpha, And we will look now at the magnetization at the time point specified, magnetization at time 1. That's just C magnetization. This is being rotated by the RF pulse by alpha degrees about x. So after time 2, at the time point 2, we have, we're rotating now about x in the rotating plane. So the y component is mz times sine alpha, and the z component is mz times cosine alpha. And now we'll just be interested in what's happening in the transverse plane, so we'll forget about the longitudinal component. We'll just consider now the transverse magnetization. This transverse magnetization will precess depending on the gradient with gamma gyy or gamma gxx. So the precessional frequency here is given by gamma times b0 plus the scalar product of g of t times r. So we'll take the gradient along y, we'll apply it here for a certain amount of time with an amplitude of n times delta gy, and we have the gradient along y. First applied negative, we'll define here the time points, we'll define this time point, that's time point number 3, and this duration between 2 and 3 shall be tau. So at this time point, between 2 and 3, the magnetization in the transverse plane, now we're just looking at the transverse plane, is the my magnetization that we had here, this magnetization, times sine of the phase, and for the x component, the x component, and for the y component, cosine of the phase that we have here. So this is the phase phase x. So if we take an influence of the gradient, we'll call this with phase. So now we will have the invert the gradient. So now the B field becomes plus gamma gxx. During this time we have the precession according to the position in our area, and so we will have a rotation. So a rotation of the magnetization along x by an angle plus phi x. So what we have here, we've written here, we've not considered the effect of the y gradient, just consider the effect of the x gradient. This gives a rotation by minus phi x. If we have now the inversion of the polarity of the gradient, this rotates the magnetization by an angle plus phi x. So this gives us a maximal signal at Te equals 2 tau, that's this time here. I will assume here for this argument that delta gy equals to 0. And now we're looking at the fourth time point. For delta gy equals 0, we have the magnetization is now given by mz sine alpha for the y component and mz cosine alpha for the z component, where we have echo formation. So we can work in these equations fully for the effect mathematically for the effect of the gradients. Now the signal at time tau or t, that is for the phasing cogradient, we have the influence of the phasing cogradient, magnetization at the start, and the influence of the readout gradient. So we have t here, tau here, so it's tau plus t is the influence of the gradient. And we can rewrite this as the signal in k-space, again with an appropriate variable transformation. So mathematically, MRI, and this is the key take-home message, MRI measures the 2D Fourier transformation of the object. That's what's being registered. What is also key is that in measuring the second spatial dimension, that requires time, and this time is strongly influenced by the T1s at hand, which are typically on the order of seconds. So this is very complicated, I understand. So understanding phase encoding is not a very easy topic. We will try to rehash the process of phase encoding under a different perspective at the beginning of next week, to look at this with a slightly different optic so we can digest this better and understand how spatial information is being encoded.